Okay, hi everyone. Firstly, I hope you had a really good holiday. As you know, as good as it could be. Anyway, I don't feel like I'm going totally insane yet. I'm still over in the UK, so that's kind of nice. And it's kind of been good just to chill at home, really. But I am missing everyone, and I'm hoping we're going to be able to go back to school fairly soon. Looking at the next part of functions, and we're only really going to spend today on this, and then from Wednesday, Friday, Saturday, we'll start looking at quadratics. We are going to have our Teams meeting on Friday, and so we'll go through a little bit of stuff there, and that'll probably take us until about mid next week, and then we'll start the next thing after that as well. Okay, so last bit on functions. So the last thing we need to look at is what an inverse function is. So I just want you to remember, and I'll send you these notes so you can print them out if you need to. A function is a type of relationship where every input results in a defined output. So that's kind of the definition that we've been working with so far. And today, when we're looking at inverse functions, this definition that we've been using so far is true, but for inverse functions, there needs to be a bit of an added layer onto it as well. So we'll talk about that in a minute. Okay, so every input results in a defined output, and you can think about that in terms of x and y values. Okay, that every x value has a distinct y value. Okay, meaning that, again, this is just revision, so you should be familiar with this already, that say for example, you have a quadratic graph. Okay, each of those x values has an individual value of y. You're not repeating by having one x value having two different values of y. We can have two x values producing the same value of y, but not one x value producing two y values. And a graph that would look like that would be one that is like this one here. Okay, so the next thing we need to talk about, which is also revision, is inverses in maths that you've commonly seen before. So we've mostly, when we talk about inverses, looking at them as operations. So where one operation undoes another operation. You know, some of the ones that you should be very familiar with are adding and subtracting, multiplying and dividing, squaring and taking the square root of a number, and likewise, you know, cubed root, fourth root, fifth root, etc. Okay, and what other ones have we done this year? I think that's about it, really. Okay, but you should be pretty familiar with all of those. Okay, what we're going to look at now, and it has the same kind of idea as an operational inverse, but a function inverse, whereby one function undoes what another function had already done. Okay, so I'm going to go back to this idea of having a machine. So here's our original function machine, where we have an input, and that results in an output. Now, if we flip this machine upside down, if we put in an output, that same output that we put in here, okay, so we flipped the whole thing upside down, turned it inside out, okay, we could start out back at our original input. Okay, and that's what an inverse function does. And just a little bit of notation for you here. This f -1, that means the inverse of function f, the inverse of f. Now, something else to note, that's not the power of -1, okay? That is something different. That's what we call a multiplicative inverse. Sorry, hard to say. And that's something that you might look at later on, but for the moment, it's not a power of -1, it's just a -1, okay? So it's f -1x, and that's the inverse of f. Okay, and that results in what we call our inverse function. Okay, likewise, same as if we can have a g of x function, we can also have a g -1. That would be our inverse of g function there. Okay, now I said at the start that we need to kind of work on this definition of a function a little bit. And that's because previously we have been able to have functions that are quadratics. Quadratics are functions, okay? You have that defined, each x value having a distinct y value. But when it comes to an inverse function, we can't have that repetition of y values. Okay, and the reason for that is again, if we go back to our machines, we can't have that output going in twice if we keep our definition of a function the same. So for example, say if we're looking at so I'll use a proper example. Say we're looking, this is our x squared function here, okay? And we know that with our x squared function, we could have an x value of -1, okay, would produce an output of 1, and an input of 1 would also produce an output of 1, okay, where we're squaring both of those. Okay, so we've got input, we're putting in -1 and we're putting in 1, and we're bringing 1 out again. All right, now if we turn that function machine upside down and we put in 1, okay, the only thing that we can start off with again here is 1, okay, because our function machine can't work out that there's two possible things that you could put in to make that. It's only going to look at that one defined thing that it could be. Okay, so when we're looking at inverse functions, we need to build on our definition, and that is that a backwards function machine or an inverse function machine will only work if the original function machine produces a unique output for each unique input. Okay, so now we need to have only one x going in to give you one y, and not like when we're talking about regular functions where you can have x giving you two of the same y. Okay, there needs to only be one of each. All right, and that becomes important when we're talking about domains, and I'll mention that in a second. Okay, so how do we find the inverse of a function? Oh, and sorry, I should apologize in advance. This will be probably quite a long video, but there's a bit to it. How do we find the inverse function? Okay, so I'm going to show you how I do it. So if we know that we've got this function f of x equals 2x minus 3, and we're wanting to find the inverse. Now, the way I do it is we would say that this function, we can let y equal 2x minus 3. Okay, now to find the inverse, all we do is we swap around the x and the y. So we let this be x equals 2y minus 3. Now we're going to rearrange this to solve for y. So we solve in the same way we solve any equations. So the first thing we're going to do is add 3 to this side. So we have 2y equals x plus 3. Okay, and then we divide through by 2. We can cancel that out. So our function is y equals x plus 3 on 2. And we can write that as the inverse. So we can say f inverse x equals x plus 3 on 2. Okay, now that's our inverse function. I'm going to show you a couple of interesting things about inverse functions, but I'm just going to get my graphs up. Okay, so here we go, there's my graphs. Okay, so here is our function f of x equals 2x minus 3, so that's one we just found. Now I've already put the inverse in here, g of x, so I'm going to turn that on. Okay, and the other thing is that I've also put in here the line y equals x. Now hopefully what you can see is that the inverse function and the original function are symmetrical around that y equals x line. They're actually reflections of each other. So if you reflected that f of x, if you've reflected it over that y equals x line, okay, you end up with the inverse, and that's a really important quality. The other thing is, I'm going to show you about that input-output thing that we were talking about before. So if I put in an input of, say, I'm going to go with 10. So if I go f of 10, okay, my output is 17. You can see that there. Now, if I put in g of 17, okay, my output is now 10. So I've gone back to my original starting value. And the other interesting thing that I want to show you is that if we put in, and I need to turn off this that y equals x line for this, but if I now take a composite function, if I do f of g of x, okay, you'll notice that that's the same as that y equals x line. I'm going to turn that back on again. Okay, so when you to a composite function of your inverse and your original, you should always end out with x as your inverse, as your combined, your composite function. Okay, and if we do the same thing, if I do g of f of x, okay, and I turn that on, that's still that same line. So it doesn't matter which way you take it, whether you do g of f of x or f of g of x, and I'll show you how you can work that out. Okay, so if we go back here, I'll show you. So if we look at f of inverse of x, so we're taking the composite function, we're putting f of inverse x into f of x. Now I hope I've left myself with enough room here. Okay, so we're putting x plus 3 on 2 in for x in f of x. Okay, so we've got two lots of x plus 3 on 2, okay, minus 3. Now, that times by 2 and the divide by 2, that can cancel out. So we're left with x plus 3 minus 3, plus 3 and the minus 3 cancel, so we're left with x. Okay, and that's that reflection line, that's that y equals x. So when you put them together, that's always what you end up with. Okay, alrighty, the next one, now this is where I said the domain comes in and is really important. So we want to find the inverse of g of x equals 2x squared. So I just want to show you, sorry, if you give me a sec, I'm just going to delete this, not duplicate, delete, or actually I'll just turn it off, it's quicker. Okay, so I'm going to put in here, what are we up to? I'll go j of x, okay, equals 2x squared. Okay, so here's our original function. Now, this is important because here you can see that for any x value, except for 0, you've got two y values. Now, with an like I said, with an inverse, you can't have that. So we're going to restrict this function to say we're only going to look at where x is greater than 0. Okay, so where x is bigger than 0. So this is what we're going to find the inverse of, because now we've got one x value for every one y value. Okay, so we're going to go back here. So same thing again. I'm going to let y equal 2x squared. Then I'm going to flip around the x and the y's. So I'm going to say x equals 2y squared. Then I'm going to divide through by 2. So y squared equals x on 2, x divided by 2. And then lastly, I'm going to take the square root of my whole function. Okay, so square root x on 2. Okay, now when I type this in, okay, oh sorry, and I should write it using proper function notation. Sorry, that's my bad. So I should say here, that means that f negative, oh no, it's g, isn't it? Sorry, g negative 1 x, g inverse x equals the square root of x on 2. There we go. All right, so if I put this in here, called k of x equals the square root of x on 2. Okay, so we can see those two functions there. So there's g of x and there's the inverse of g of x. And if I put that y equals x line in again, we can see that again they're symmetrical or reflections of each other. Okay, so they're reflected around that line y equals x. All right, so that's fine. Okay, so again, we're just going to kind of do the inverse, the composite function inverse, just to check. In this case, we're going to do g negative 1 of g of x. Okay, so we're going to put g of x into g negative 1 of x. So we're going to have the square root of 2x squared, okay, because that 2x squared has gone in for x, on 2. Now again, those 2's cancel, okay, and we're left with the square root of x squared, okay, which is just x. Okay, so that is definitely our inverse function, 100% for sure. Okay, last one, and then we're going to stop, especially because this video is going to cut out. So we've got h of x equals 1 over x squared, again where x is greater than 0. Okay, so we're restricting that domain so that we can find the inverse. All right, we have flipped around x and y. So we've got 1 over y squared. We're going to multiply by y squared, get that out from under the fraction. Okay, so we've got y squared equals, y squared times by x equals 1. Okay, we're going to divide through by x to get that by itself. So y squared equals 1 over x, okay, and therefore